This video looks at solubility equilibria. By the end of this video, you should understand the system described by the solubility product constant, be able to calculate KSP from solubility info, be able to calculate solubility from KSP values, use the ion product to predict whether precipitation will occur, and understand the common ion effect. Solubility equilibria represents the system that exists when we have a solid dissolved in a liquid to form an aqueous solution. As you probably know, the term solubility refers to the maximum amount of solid that will dissolve in a given amount of water at a particular temperature. When we've reached the point where we've dissolved this maximum amount, we have a saturated solution. Note, often the best way to tell if a solution is saturated is if you actually see solid at the bottom. This means that all of the solid that can dissolve has dissolved, and the rest has simply settled to the bottom in solid form. The solubility product constant, or the KSP, is the equilibrium constant that describes the solubility of a salt. Consider the dissolving of calcium hydroxide, represented in the beaker to the right. When solid calcium hydroxide is placed in water, it dissociates into a calcium 2+ ion and 2 hydroxide ions. This is an equilibrium system because as long as we have a saturated solution, the rate of solid dissolving is equal to the rate of aqueous ions recrystallizing to form solid. The KSP expression for this reaction is written just like any other K expression. Recall that we do not include solids in our K expressions since their concentration does not affect the equilibrium. Since all solubility equilibria involve solids in the reactant side, we will never have a K value with a denominator. Our KSP expressions will always include just the products. Let's consider what the size of the KSP value means. Here's the KSP value for 3 common salts. Which one do you think is the most soluble at 25 degrees Celsius? If you said calcium carbonate, you're correct. Since it has the largest K value, that means it's the most product favored, or it means that it has the highest concentration of dissolved ions at equilibrium. There's 2 main calculations you'll need to do with KSP. First, we'll look at how to calculate the KSP value from solubility data. Copper 1 bromide has a solubility of 2.0 times 10 to the negative 4th moles per liter at 25 degrees Celsius. This means that in every liter of water, I can dissolve a maximum of 2.0 times 10 to the negative 4th moles of copper bromide. Let's calculate the KSP. First, we'll write the reaction, which is just a dissociation equation for copper bromide. Then we'll write our KSP expression. Again, do not include the reactant since it's a solid. Now, since we know how much copper bromide dissolves in 1 liter, we know the concentrations of each of the ions at equilibrium. If 2.0 times 10 to the negative 4th moles of copper bromide dissolves, we will get 2.0 times 10 to the negative 4th moles of copper and 2.0 times 10 to the negative 4th moles of bromide, since it's a 1-to-1 ratio. Therefore, we can plug these values into our KSP expression and solve, obtaining a KSP of 4.0 times 10 to the negative 8th. Again, since this is a K value, no units are required. Here's one to try on your own. Pause the video here, and when you come back, I'll reveal the answer. Make sure you pay attention to your units in this one. Welcome back. Here's what you should have gotten. Notice the trick here. You were given solubility in grams per liter, which had to first be converted to moles per liter. Also, unlike the previous example, we did not have a 1-to-1 ratio for each of our ions. We formed 3 times the amount of chloride ion as we did aluminum ion. Therefore, we had to multiply our solubility times 3 to get the concentration of chloride ions at equilibrium. Now let's go the other way and try calculating solubility from KSP. Here we're told that the KSP value for silver iodide is 1.5 times 10 to the negative 16th at 25 degrees Celsius, and we're asked to calculate the solubility. We're going to again start by writing the equation and then writing our K expression. However, now we actually know the value for K, so we can go ahead and plug that in. Since we know that silver and iodide exist in a 1-to-1 ratio, we know they'll be equal to each other. Therefore, I'm going to call each of them X. This gives us the following expression. Solve for X, and we're given a concentration of 1.2 times 10 to the negative 8th of both silver and iodide at equilibrium. This also means that the solubility of silver iodide is 1.2 times 10 to the negative 8th moles per liter. Here's an example for you to try on your own. Pause the video here, and when you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. Notice in this case, we had a 2-to-1 ratio between our ions. Therefore, we had to both double and square the Br- concentration. It's also possible to use a value called the ion product to determine if precipitation will occur when two solutions are mixed. The ion product is essentially the Q value for KSP expression. Recall that we calculate the Q value by plugging in current concentrations in our equilibrium expression to see whether or not the reaction is at equilibrium, and if not, which direction it needs to proceed. If we find that Q is greater than K, this means that our ion concentrations are too high. Therefore, the reaction will need to proceed in the reverse direction to establish equilibrium, and precipitation will occur. If Q is less than K, this means that our ion concentrations are less than the maximum allowed in that volume of water, and our reaction will proceed to the right. Therefore, no precipitation will occur. If Q is equal to K, that means the solution is exactly saturated. We've dissolved the maximum amount of ions possible in that volume of water. Let's look at an example. Suppose that 0.010 moles of lead-2 chloride are dissolved in 150 milliliters of water. The solution is then cooled to 25 degrees. Will the PbCl2 precipitate? And we're also given the KSP value at 25 degrees Celsius. First, let's start by writing an equation as always, and then our equilibrium expression. This is always our starting point. Now we need to determine ion concentrations. Since we dissolved 0.1 moles in 0.15 liters, we can calculate concentrations for each. Notice that 0.01 moles of PbCl2 yields 0.02 moles of chloride, since there's 2 moles of chloride for every 1 mole of PbCl2. This gives us our current concentrations. The question is whether or not these will be equilibrium concentrations once we've cooled the system down. So, let's determine Q. We do this by plugging our current concentrations into our K expression and solving. Here we find that Q is equal to 1.2 times 10 to the negative third. Compare this to our K value, and we find that Q is greater than K, which means at this new cooler temperature, the ion concentrations are too high, so some precipitation must occur. The reaction must proceed in the reverse direction. Here's an example to try on your own. Pause the video here, and when you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. In this case, Q turned out to be less than K. Therefore, no precipitation will occur. Finally, let's look at the common ion effect. The common ion effect tells us that the presence of a common ion will affect salt solubility, and this is based on the Chatelier's principle. Consider the equilibrium system shown here between solid calcium fluoride and aqueous calcium fluoride. If calcium fluoride is added to a solution that already contains a common ion, calcium or fluoride, the equilibrium position will have to shift to the left to compensate for the extra ions. It's the same thing as increasing the concentration of one of our products. This causes our equilibrium position to shift to the left. This means that calcium fluoride is less soluble in a solution that contains a common ion. This can also be applied to pH. The pH of a solution can affect the solubility of a salt due to the common ion effect. For example, consider the dissolving of magnesium hydroxide. If we try to dissolve magnesium hydroxide in a basic solution, meaning a solution where significant amounts of OH- are already present, our equilibrium position will shift to the left. Therefore, magnesium hydroxide will be less soluble in basic solutions. On the other hand, consider the case of the dissolving of silver phosphate. Here, an acidic solution will actually increase the solubility because the H+ ions will be able to react with the phosphate ions to form HPO4 2-. This will actually cause the equilibrium position to shift to the right, and the solubility of silver phosphate will increase in acidic solution. That brings us to the end of this video. Let's review our goals. First, we looked at the system described by solubility product constant, that between the dissolving of a solid and the recrystallizing of aqueous ions. Then we learned to calculate the KSP from solubility info and calculate the solubility from KSP values. Then we used the ion product to predict whether precipitation will occur. And finally, we took a look at the common ion effect.